There is a particular kind of dream that humanity has carried for generations, a vision so seductive, so cinematically compelling, that it has become embedded in the very marrow of our cultural imagination. It is the dream of the starship, the sleek, magnificent vessel cutting through the darkness between suns, carrying explorers across the light years, bridging the cosmic distances that separate civilizations, flourishing on worlds we have not yet seen. We have painted this picture in 1,000 stories, inscribed it into the collective mythology of our species, and somewhere deep in the architecture of our hope, we have come to believe it as a kind of destiny, that if we simply build the ship correctly, if we engineer the hull with sufficient precision and ignite the engines with sufficient power, the stars will open themselves to us. That the universe is waiting, patient, and welcoming for us to arrive. I want to dismantle that dream tonight, not with cruelty, but with something far more arresting, with the cold, luminous arithmetic of physics itself. Because the truth that the equations reveal is not the story of engineering triumph over distance. It is the story of a universe that has constructed, in the very fabric of space-time and thermodynamics, a set of absolute, permanent, mathematically ironclad barriers between every solar system that has ever existed. And what is profound, what is genuinely awe-inspiring when you sit with it, is that these barriers were not built to imprison us specifically. They emerge, inevitable and indifferent, from the same beautiful physical laws that allow atoms to form, stars to burn, and biology to organize itself into beings capable of asking the question in the first place. The trap is not personal. It is simply the universe being itself, and the universe, it turns out, is extraordinarily, mercilessly good at keeping its inhabitants home. Let us begin where all serious confrontations with cosmic travel must begin, not with rocket fuel or warp drives or exotic propulsion fantasies, but with a number, the speed of light, 299,792,458 meters every single second. A number so large that it outpaces all ordinary intuition. And yet, against the scale of interstellar distances, this number is humiliatingly, heartbreakingly small. The nearest star system beyond our own, the Triple System, anchored by Alpha Centauri and including the small red dwarf Proxima Centauri, sits approximately 4.24 light-years from Earth. This means that even a beam of massless light, the fastest information carrier that physics permits to exist, requires 4.24 years to cover that distance. A civilization attempting to send a physical object, a ship with mass, with structure, with crew or circuitry, cannot even theoretically travel at the speed of light. That is not a pessimistic engineering forecast. It is a logical consequence of special relativity. And what special relativity demands of any massive object that attempts to approach that cosmic speed limit is a price so catastrophic, so geometrically monstrous, that no energy budget in any plausible physical universe could ever pay it. Consider what happens when you attempt to accelerate a mass toward light speed. As the velocity increases, the relativistic momentum of the object does not increase linearly, the way classical Newtonian intuition would suggest. It increases according to the Lorentz factor, a term that begins innocuously enough at low velocities but transforms into something savage at high ones. At 10% of the speed of light, the Lorentz factor is approximately 1.005, barely noticeable. At 50%, it rises to 1.15. You are carrying about 15% more effective mass than you started with. At 90% of light speed, the Lorentz factor climbs to approximately 2.3, meaning the object's relativistic momentum has more than doubled. At 99%, the factor reaches 7. At 99.9%, it surpasses 22. At 99.99%, it exceeds 223. The pattern is not merely steep, it is asymptotic. The curve approaches an infinite value as velocity approaches the speed of light. And what this asymptote means physically is that to reach light speed, you would need to supply an infinite quantity of energy to a finite mass. Not a very large quantity, not a quantity beyond current technology, but theoretically achievable with future engineering. An infinite quantity. The universe does not offer exceptions to this on the basis of civilizational advancement or engineering sophistication. The mathematics does not negotiate. Infinite energy is not a resource that any physical civilization, no matter how ancient, no matter how intelligent, no matter how deeply it has plumbed the secrets of particle physics, can accumulate or deploy. This is what I mean when I describe special relativity as an unbreakable physical padlock. It does not merely make interstellar travel difficult. It makes the upper boundary of interstellar travel velocity mathematically impossible to reach, and it makes the energies required to even approach that boundary so catastrophically large that they expose the true nature of the cosmic quarantine we are discussing. We are not separated from other civilizations by a gap in technology. We are separated by a gap in available energy that scales toward infinity. The padlock is not waiting for a better key. It is waiting for the physical impossible, and the physical impossible is, by definition, permanent. Let us construct an analogy, because the mathematics, as beautiful as it is, benefits from a companion image that carries its brutality into the imagination. Imagine a crystal sculpture, not merely any decorative object, but a work of extraordinary, meticulous engineering. A structure carved from a single flawless substrate, its atomic lattice aligned with a perfection that would humble any craftsperson alive. Every facet ground to a surface smoothness measured in individual atomic diameters. Every internal geometry optimized according to principles of structural integrity that represent the pinnacle of material science. It is, in every measurable sense, the most magnificently constructed physical object its creators have ever produced. Now load this sculpture into a cannon. Not a modest piece of artillery, but a colossal accelerating device of supreme engineering achievement, capable of imparting to the sculpture a velocity that approaches some meaningful fraction of what physics permits. And aim it directly at a mountain. Not soft soil or crumbling sedimentary rock, but a mountain of solid, dense, ancient granite, crystalline and unyielding, a mass of interlocked mineral bonds that has endured for billions of years. What happens when the sculpture meets the mountain is not a function of the sculpture's quality. The fact that it is flawlessly polished is irrelevant. The fact that the cannon is a masterpiece of engineering is irrelevant. What happens is determined entirely by the physics of kinetic energy transfer at the moment of impact. The kinetic energy stored in the moving sculpture, which scales with the square of its velocity, is deposited almost instantaneously into the sculpture's atomic structure. The bonds between atoms, which define the sculpture as a sculpture rather than as a dispersed collection of individual atoms, cannot absorb that energy without breaking, and so they break. Every bond, almost simultaneously, in a cascade of atomic disruption that transforms the most perfectly engineered object in the civilization's history into a fine cloud of ionized matter drifting outward from a crater in the granite face. The mountain did not care about the sculpture's quality. The mountain never does. Now understand that the interstellar medium is that mountain, and the spacecraft, regardless of how magnificently its civilization has constructed it, is always the crystal sculpture. Space between the stars is not empty. This is one of the most consequential misunderstandings in popular scientific imagination, and correcting it is essential to grasping why interstellar travel is not merely difficult but physically catastrophic. The interstellar medium is a diffuse but pervasive distribution of matter, gas and dust and plasma threaded through the apparent void between stellar systems. On average, the interstellar medium contains approximately 1 hydrogen atom per cubic centimeter in the regions near our galaxy's midplane. In denser molecular cloud regions, this number climbs orders of magnitude higher. Even in the most evacuated stretches of interstellar space, there are stray particles, lone protons, drifting dust grains measured in micrometers, the scattered debris of stellar formation events that occurred billions of years ago. Under ordinary conditions, the presence of 1 hydrogen atom per cubic centimeter is inconsequential. We do not notice it. It exerts no meaningful force. It poses no threat. But all of that changes with a violence that requires careful contemplation to fully appreciate when you introduce a spacecraft moving at an appreciable fraction of the speed of light. At 1% of light speed, approximately 3,000 kilometers per second, a single hydrogen atom encountered by the hull of a spacecraft carries a kinetic energy in the reference frame of the ship of approximately 400 million electron volts per atomic mass unit. To place this in context, the threshold for nuclear spallation reactions, the process by which a high-energy particle literally chips nuclear fragments off of atomic nuclei, begins at energies around a few tens of MeV per nucleon. At 1% of light speed, every single hydrogen atom that strikes the hull of the spacecraft is arriving with energy roughly an order of magnitude above the spallation threshold. It is not merely bouncing off. It is initiating nuclear reactions in the material it strikes. Now consider what this means for the hull itself. A spacecraft traveling through the interstellar medium at 1% of light speed is, from the perspective of its own hull material, being continuously bombarded by a particle beam of the intensity that would be associated in a ground-based facility with a major particle accelerator. Each impact deposits energetic particles into the hull lattice. These particles initiate spallation cascades, fragmenting nuclei, generating secondary radiation, producing radioactive isotopes within the hull material itself. Over time, the hull is not merely damaged. It is systematically transformed. The atomic structure of the material is being rewritten, bond by bond, nucleus by nucleus, into something increasingly fragile, increasingly radioactive, increasingly unlike the engineered structure it was designed to be. At 10% of light speed, the situation becomes incomparably worse. The kinetic energies per nucleon climb by a factor of 100. You are no longer discussing nuclear spallation alone. You are discussing the production of hadronic showers, cascades of secondary particles generated when primary cosmic ray equivalent projectiles strike the hull material with energies measured in tens of billions of electron volts. The hull material does not merely degrade, it begins, atom by atom, to evaporate forward into a spray of secondary radiation, effectively ablating from the front face of the vessel as if it were being subjected to a continuous, omnipresent plasma torch. This is what I mean when I say that high-speed interstellar travel transforms the vacuum itself into a kiln. The emptiness between stars is not a passive, neutral medium through which you simply need to be patient enough to travel. At the velocities that would make interstellar journeys plausible on any civilizational timescale, it becomes an active, relentless, high-energy processing environment that attacks every known material structure at the most fundamental physical level available to it, which is to say, at the level of individual atomic nuclei. Engineering cannot circumvent this. There is no material composed of atoms in any known or theoretically permitted configuration that does not experience nuclear spallation when subjected to particle impacts above the spallation threshold. The atoms themselves are the vulnerability,